In this problem, we will deal with transfer functions, DFTs, and inverse DFTs. The first thing this problem asks us to do is find the transfer function for the exact inverse of the filter. What you would do to begin that process is find the frequency domain representation of your filter h of n. Since it is just a sum of shifted and scaled delta functions, you find that on a lookup table. Then to take the inverse of that, you would get 1 over 1 minus 0.1 times z to the negative 64th. This is because the inverse of that function is just 1 over h of z. Next, we're asked to find the DFT coefficients for g of k. To do that, you take your original h of z, and for z, you plug in e to the j omega, which would give you 1 minus 0.1 times e to the negative j omega times 64. By using the definition of a DFT, we find that h of k is equal to 1 minus 0.1 times e to the negative j pi k, since a lot of our terms end up canceling out. Since g of k is equal to the inverse of our filter h of k, you would then do 1 over h of k. And note that this is only applying for k greater than 0 but less than 127, because we've done the 128-point DFT. We are then asked to determine g of n, which is the inverse DFT of g of k. To do that, you would multiply your numerator and your denominator by your complex conjugate of your denominator, which would give you 1 plus 0.1 times e to the negative jk all over 1 minus 0.1 times e to the negative j2 pi k. You would then be able to split up this fraction and use a lookup table to find what your values for g of n should be. That will leave you with g of n being equal to 100 over 99 times delta n plus 0.1 delta n minus 64, showing that just like your original filter, your inverse filter is also